Welcome to our new video of PyML Studio on vision transformers. After covering the ViT paper in the previous video, now we are going to look at two different variants of ViT that has somewhat similar objective. One of them is called Data Efficient Image Transformers or DeiT, and the other one is called Tokens-to-Tokens ViT. Before we start with these two methods, let's have a quick recap of ViT. As we covered in the previous video, ViT splits the input image into a sequence of patches, or also called tokens. We feed this sequence of tokens into a linear projection layer that outputs token embeddings, and then we prepend them with a special class token at position 0. And after that, we add position embeddings and feed the results through the standard transformer. Finally, we extract the embeddings at position 0 and feed them through a classification head. ViT was designed to introduce minimal inductive bias and learn everything from scratch. While this is powerful, but the drawback is that it needs lots of training data. So the original ViT, which we refer to as vanilla ViT, needs to be trained on a massive image dataset such as JFT 300 million. So as we continue our journey to vision transformers, here is the list of different variants of ViT. In this video, we will cover the first two methods, DeiT and T2T ViT, and leave the rest for future videos. Note that both DeiT and T2T ViT are designed to be trained on mid-sized datasets such as ImageNet 1K. Starting with our first model, DeiT or Data Efficient Image Transformers. DeiT is designed to resolve the limitation of ViT, that is, the need for very large training data. And as we'll see in this video, DeiT can outperform vanilla ViT and CNN models when using only ImageNet for pre-training. The key idea of DeiT is a student-teacher knowledge distillation technique that we'll discuss in details. So let's have a brief overview of knowledge distillation first. In knowledge distillation, we have two models, a teacher model and a student model. The teacher model is usually a more complex model, and its role is to guide the training of the student. The student model is typically a smaller and more efficient model, and its objective is to learn to mimic the behavior of the teacher. There are two modes for training the student. In one mode, the teacher model can be trained a priori and just used as a frozen model for training the student. And the second mode is to simultaneously train both teacher and student together. For training the teacher model, we use the ground truth labels, but the student network gets its targets from the output of the teacher. And there are two ways to obtain targets for the student. One, soft distillation, which means we use soft targets or probabilities from the teacher and use them to train the student. And the second option is hard distillation, which is when we calculate hard labels from the decisions made by the teacher. The DeiT paper has explored both of these options. So now let's dig into knowledge distillation framework that is proposed by DeiT. For soft distillation, the authors proposed the following loss function for training the student. In this equation, Zt and Zs are the logits of teacher and student respectively, and sigma denotes the softmax function that converts logits to probabilities. The first term is a regular cross-entropy loss using the ground truth labels y, and the second term is the KL divergence between the probabilities of the student and teacher. Lambda and tau are the hyperparameters, where lambda is the balancing factor between the two loss terms, and tau is the temperature that controls the smoothness of probabilities. For hard distillation, the authors propose to use two cross-entropy terms with equal contributions. The first term is the same as before, using the ground truth labels y, and the second term is using the hard labels that are predicted by the teacher, so they are obtained by applying argmax to the logits of the teacher. The paper compares the performance of the soft distillation and hard distillation, and in fact, hard distillation is significantly outperforming soft distillation. Here is the proposed architecture for the student model. They added a new token called Distillation token that is appended at the end of the input sequence. So now we have class token at position 0 and Distillation token at the last position. The final embeddings from both of these tokens contribute in the loss function for training. So the embeddings from the class token are used in the first loss term, that is cross entropy with the ground truth label, and the embeddings from the Distillation token are used in the second loss term to learn from the output of the teacher. And at test time, we have three options for feeding embeddings to the classification head. First option is to use the class embeddings only. The second option is to use the distillation embeddings only. And the third option is to use a late fusion approach and taking both class and distillation embeddings together. The authors have experimented with all three options and found out that late fusion outperforms the other two approaches. This table shows three DeiT architectures and their details. DeiT B has similar architecture as in ViT B for base, and DeiT S and DeiT TI are two smaller architectures. Notice that DeiT TI for tiny has only 5 million parameters. And finally, here is the results that compares the performance of a student model trained with different teacher models. The important point here is that when a student is trained using a ConvNet-based models, it performs better than if it is trained using a ViT-based model. In other words, the student learns better from a CNN than from a ViT. So now we move to the second paper, that is Tokens-to-Token ViT. Similar to the previous paper, the motivation for this paper is to build a vision transformer that can outperform CNNs when trained on a mid-sized dataset. This paper hypothesizes two reasons for why ViT trained on mid-sized dataset has inferior performance compared to the CNNs. The first reason is that tokenizing an image into sequence does not capture the inherent structure of images. And the second reason is due to the redundancy observed in ViT features, which we will see in the next slide. T2T ViT overcomes these issues using a recursive tokenization process and a well-designed backbone structure. This figure visualizes the features from a trained ResNet model and a vanilla ViT. As you can see, the vanilla ViT has some invalid features shown in red, which leads to limited feature richness. But the proposed model has resolved this issue, so now let's see how it works. The proposed tokenization process has two steps. Given an input sequence of tokens that has two dimensions like n by d, we first reshape that to form a 3D image-like structure with height times width times depth, where depth is the number of channels. Then, in the next step, we perform a soft split that breaks this 3D structure into overlapping patches, with patch size k and overlap s. To understand this process, let's consider the example shown here. The input is a sequence with dimensions 16 by c, where c is the number of channels. In step 1, we reshape it to make a 3D tensor of size 4 by 4 by c, and then we perform soft split with patch size equals 2 and overlap equals 1. This will result in 9 patches, each covering a 2 by 2 region. So we aggregate them by concatenating their embeddings, resulting in a new sequence of size 9 times 4c. So you can see that we were able to reduce the sequence length from 16 to 9 in this example. Here is the full architecture with two major components. First, we have the T2T module shown on the left, and on the right we have the backbone. T2T module is a stack of T2T tokenization layer followed by a transformer layer. So the length of the sequence in T2T module decreases after each tokenization layer. But when the sequence reaches the backbone, its length is fixed. And from here we add the position embeddings as well as the special class token. For the T2T module, they proposed a depth of n equals 2, which means it is composed of 2 transformer layers and 3 soft split layers. So for example, with patch size of 7, 3, and 3, and overlaps 3, 1, and 1 for these soft splits, feeding an input image of size 224 by 224 results in an output size 14 by 14. This 14 by 14 will be the final patch size for creating a sequence that is fed to the backbone. This table shows different architecture details. While the depth of T2T module are the same, but changing the batch size and overlaps in the T2T module results in different architectures. And the models are denoted by their final output dimensions. So, for example, T2T ViT 19 means the T2T module reduces the image size from 224 by 224 to 19 by 19. For the backbone, they have also experimented with different architectures by changing the hidden dimensions through the layers in the backbone. And finally, here is the results of different T2T models compared to the vanilla ViT as well as DeiT. All models are trained on ImageNet 1K, which is a mid-size dataset. And the results indicate that T2T models outperform both vanilla ViT and DeiT, thanks to the proposed tokenization process that embeds the inherent structure of images into the sequence. So in this video, we cover two variants of the ViT model called DeiT and T2T ViT with similar objective. Both of these methods have been able to train vision transformers on mid-sized datasets and still outperform CNNs. In future videos, we will cover other variants such as Swin, Dino, and Clip. So stay tuned and thanks for watching.